Okay, so in this lecture, we will apply the PFR mole balance. So PFR mole balance the forms for that, written in terms of molar flow rates, we've said dFA dV is equal to RA, or in other words, the rate of change in the molar flow rate of species A is equal to the rate of generation of A. If species A is a reactant, then we know that the rate of generation of A is negative. And therefore, FA decreases down the reactor volume. Since the rate of change of the flow rate of A with respect to reactor volume is negative in that case, it's going to decrease with reactor volume. In contrast, if A is a product, the rate of generation of A is positive. So FA increases down the reactor volume. We could also write this mole balance in terms of conversion. So in doing that, we get to dXA dV is equal to the rate of consumption of A divided by the inlet molar flow rate, where again, this molar flow rate is at the reactor inlet. In this case, if A is a reactant, then the rate of consumption would be positive, and that would mean that the conversion would grow. It would get larger over or as we proceed down the reactor volume. So notice that this balance is written with respect to the rate of consumption of A. That is because the conversion, well, it'll say, let's go back and say if A is a reactant, then minus RA rate of consumption is positive. So the conversion of A, XA, increases as the reactor volume increases. So again, it's always proper accounting for your different variables. So your flow rate of A, if A is a reactant, is going to decrease, but your conversion of A, the more A that's reacted, is going to increase. So just like we've said with the other reactors, if you're solving a reactor design problem for a prototypical PFR, you can just write down the form of the balance that you intend to use, whether that be in terms of F or X. The important thing there then becomes making sure that your entire balance is written in either F terms or X terms and not convoluting them. You don't have to rederive the balance each time. With following exceptions, one is if we ask you to derive the balance, then you should derive it. And two is if it's not a prototypical, and this should say PFR. So, for example, if it's a membrane reactor, for example, in that case, you can't use the PFR mole balance for the membrane reactor because it's not valid for that reactor. Or if one of the assumptions that we had made for the PFR were not applicable to your system, then the PFR mole balance probably isn't applicable either. But if you have a prototypical PFR, you may just write down the correct form of the balance. So let's do an example. So the reversible reaction, A goes back and forth to B, is carried out isothermically and isobarically in a PFR. The equilibrium constant at the reaction temperature is equal to 5.8. The overall conversion is 0.55. A second PFR that is identical in every way to the first PFR is placed downstream of the first PFR so that the two PFRs operate in series. Determine the overall conversion for the system. Pure A is fed in both cases. So let's start this out by drawing the system. So we have a PFR. This is a tubular reactor. So what we have going on is we at the reactor inlet, we have A coming in, pure A. And then coming out of the reactor, we would have A and B, FA and FB. And if you recall, we talked about how PFRs operate. So once the reactants enter the reactor at the inlet, they start reacting. The concentration varies continuously down the length of the reactor. So this is the length of the reactor. We also said we could call this the volume of a reactor, since at any point along the length we could multiply by the cross-sectional area and get the volume. We've said that at any point along here, you can take a volume cross-section and we have perfect mixing within that cross-section. However, if you move to the left or the right even a little bit, then the concentration is going to be different. So we have continuous variation down the length of the reactor, but at any point along the reactor, we have perfect mixing in the radial dimension. So as we go down the length, the concentration of reactants is getting smaller, and as the concentration of the products is getting larger, and also the conversion is getting larger. So here what we need to do is solve the case where we have a single PFR carrying out this reversible reaction, and then use the information to assess the situation where we have two PFRs in series. So let's work on the first PFR first. This is giving information in terms of conversion, so I'm going to write down the mole balance, and I'm going to write down the form in terms of conversion. So dXA dV is equal to minus RA divided by FA naught. And now I need a rate law, so I need to substitute something in here. So I'm going to assume elementary kinetics. And so then that would say that my rate law is going to be equal to KAF CA minus KAR CB, or I can simplify that, KAF CA minus CB divided by KC, where Kc is the equilibrium constant. And a really good reason to do that for this problem is because we're given a value for that. So this is my rate law. However, I can't leave these concentration terms as R because I have written my mole balance in terms of conversion. That means I need to convert these concentration terms into functions of conversion. I'm not told whether this is a gas phase reaction or a liquid phase reaction, but it doesn't matter because the number of moles is the same on both the reactant and product side, so I don't have to worry about a volumetric flow rate change. Because of that, I can write Ca is equal to Ca naught 1 minus Xa. And I can also say, since B is not fed to the reactor, I can say Cb is equal to Ca naught Xa. So now I have these terms, or the concentrations in terms of conversion, and I can substitute that in to my mole balance. And I'm going to simplify this a little bit further to get actually, let's say 1 plus Xa, and I'll say minus 1 divided by Kc. And you'll see why I've set it up that way in just a second. Okay, so now, simple enough, I need to separate the variables and solve. This is going to be equal to KAF, CA naught, V divided by FA naught. So I can integrate this now. I'm going to integrate from 0 to 0.55. And this will give me a number on this side. So I'm actually going to use appendix A1. So in appendix A1, there is a definite integral formula that says the integral between 0 and some value x of dx divided by 1 plus epsilon x is equal to 1 divided by epsilon natural log. Let me redo that. Natural log of 1 plus epsilon x. In this case, so here, epsilon is going to be equal to minus 1 over kc. And x equals 0.55. So I can substitute these values into this expression and get a value. Doing that, I get the value 0.883. So that's what this integral is equal to. So that means that that is going to be equal to my forward rate constant times my initial concentration times my volume divided by FA naught. So I'm not given any of these quantities, so I don't know what any of them are specifically. I do know, however, if I take them all together in this combination, then I get this value 0.883. So now that's for my single PFR case. Now I want to think about the scenario where I have two PFRs in series. So if I think about what that looks like, I have my first PFR, A entering, A and B coming out, going into a second reactor. This is going to be an identical reactor. And then A and B coming out of that second reactor. Now, when I put these two reactors in series, really what this is going to look like is just one big PFR. And I can demonstrate that if I go back to a Levenspiel analysis. So if I just draw a Levenspiel plot, and if we are looking at a PFR case, and I take, I have one PFR that goes up to some conversion, and then I have a second PFR that goes up to the next conversion. So the volume of the two PFRs in series is going to be identical to the case where I just had one single PFR. Now in contrast, if I had the CSTR case, if I pick a place where I have a conversion, and then I say I want another point where I have a second conversion, in that case, the volume of the two CSTRs in series is going to be different than the volume if I had one single CSTR. So if I had a single CSTR getting to this conversion, it would be all of this area. The two CSTRs in series, I have this area versus plus this area. So you see how this is different than the case where I have two PFRs in series. So this is useful. So I just solved this problem for one PFR And now I basically have to go back and say, what if that volume of the PFR was double? What conversion would I get? And so that is somewhat simple. I've already done all the balances. Basically, if I double my volume, then, and these quantities all stay the same, then basically what I'm doing is I'm doubling this value. So I'm going to write that down. So I'm going to have, in this case, 1.766. And then this is going to be equal to my mole balance term. So in this case, I'll have 0 to x. X is unknown. dxa divided by 1 plus xa negative 1 minus 1 divided by kc. And I know what this integral is equal to. It's going to be equal to 1 divided by epsilon, natural log of 1 plus epsilon x, where epsilon equals negative 1 minus 1 divided by kc. And this time I'm going to solve for x such that I get a value of 1.766. So I basically I'm solving this formula. 1.766 is equal to this equation. This is an algebraic solution. I can solve this and I get x is equal to 0.75. So I get a bit more conversion by doubling my PFR volume.